If you were to drive straight up from the surface of the Earth, you would find yourself leaving the planet's atmosphere in just over an hour. This might sound like science fiction, but the idea is grounded in the principles of physics and the structure of Earth's atmosphere. To understand how this works, it's important to grasp the scale of the Earth's atmosphere and the speed at which an object would need to travel to escape it. The commonly accepted boundary between Earth's atmosphere and space, known as the Kármán Line, lies about 100 kilometers, 62 miles, above sea level. While it may seem like a short distance when considering the vastness of the universe, it is still far enough that the physical laws governing the Earth and its atmosphere begin to change significantly. To reach space by driving directly upwards, you would need a vehicle that could counteract the Earth's gravity. The force of gravity at the Earth's surface pulls objects downward, requiring a tremendous amount of energy to overcome. This energy is typically provided by rocket engines, which generate thrust powerful enough to propel an object into orbit or beyond. However, if we imagine a hypothetical vehicle that could maintain a constant upward trajectory, it would have to travel extremely fast, far faster than any car on Earth could ever go. The key to understanding this lies in the concept of escape velocity, which is the minimum speed required for an object to escape the Earth's gravitational pull without further propulsion. This speed is about 11.2 kilometers per second, about 25,000 miles per hour. While this is not the same as the speed a car would need to reach in order to break free from Earth's atmosphere, it helps to illustrate just how much speed is required to leave Earth's gravitational influence. Driving straight up would require an incredible amount of energy. However, unlike a rocket that accelerates continuously, a car would encounter many obstacles as it ascended into the atmosphere. The first hurdle would be the Earth's troposphere, the layer of the atmosphere closest to the surface. This is where weather phenomena such as clouds, storms, and turbulent air currents occur. As the car ascends through the troposphere, it would face increasing air resistance, also known as drag. The higher the altitude, the less dense the air becomes, and drag decreases. However, the initial few kilometers would be incredibly challenging, as the car would have to fight against the thickest part of the atmosphere. If a car could somehow accelerate to 11.2 kilometers per second, it would quickly encounter the stratosphere, where the air becomes significantly thinner. Above the stratosphere, there would be no air to create resistance, which might allow the car to continue its ascent more easily, but the vehicle would still have to contend with the loss of oxygen, requiring a system to support life and combustion, even though you might reach the Kármán Line in just over an hour if you could travel fast enough. There are additional layers to the concept of reaching space. Simply crossing the boundary does not mean you are in orbit or free from the Earth's gravitational pull. The Earth's gravity extends far beyond the Kármán Line, gradually weakening the further you get from the planet's surface. Achieving orbit is a completely different challenge. While reaching space is about crossing a particular altitude threshold, orbiting the Earth requires horizontal motion at incredibly high speeds. This horizontal velocity is what keeps satellites and spacecraft in orbit, as they continually fall towards the Earth but never actually reach the surface due to their high speed. So, while the concept of driving straight up sounds like a direct route to space, you would have to consider the logistics of reaching orbital velocity and the complexities of maintaining life-supporting conditions in such an extreme environment. Despite these challenges, it's interesting to think about the potential for future space tourism and human transportation beyond the Earth's surface. Companies like SpaceX, Blue Origin, and Virgin Galactic are working on making space travel a reality for civilians. These companies have taken a giant leap toward commercial spaceflight with suborbital flights, where passengers can experience a brief moment of weightlessness and see the curvature of the Earth from space. While these trips currently last only a few minutes, they represent the beginning of what may one day become regular travel to and from space. These space tourism companies aim to make space accessible, but the technology needed to reach even low Earth orbit, LEO, for longer durations is still a work in progress. A vehicle capable of reaching the Kármán Line would need advanced propulsion technology and a solid understanding of space travel logistics. One of the most significant breakthroughs that would make driving to space possible would involve advancements in propulsion technology. Current vehicles, including rockets and spacecraft, use powerful liquid and solid rocket engines to generate enough thrust to break free from Earth's gravitational pull. However, these engines require vast amounts of fuel and can be quite inefficient, particularly when considering long-term human space missions. In order to make space travel more efficient, new propulsion systems are being researched, such as ion drives, nuclear propulsion, and even potential methods of harnessing solar power. These methods could, in theory, allow for faster and more cost-effective travel to space, making the concept of a vehicle that could drive straight up seem more plausible. As technologies continue to improve, the boundaries of space travel will likely expand, making it increasingly possible to think of space as a reachable destination not just for astronauts but for ordinary civilians as well. The scientific exploration of space also relies on space stations, which are platforms placed in orbit around the Earth for research and experimentation. The International Space Station, ISS, for example, is a large structure that orbits the Earth at an altitude of around 400 kilometers. Astronauts aboard the ISS conduct experiments in microgravity and test new technologies for space exploration. The idea of traveling straight up to space touches on the infrastructure that has already been developed for human life and exploration beyond Earth. As space stations become more advanced, they may serve as stepping stones for longer journeys into the cosmos. The success of these stations will depend on our ability to solve some of the challenges associated with space travel, such as radiation exposure, life support, and the physical effects of prolonged weightlessness. In the future, humanity may be able to create a world where travel to space is as commonplace as flying across the globe. But for now, the journey to space is an extraordinary feat of human engineering and determination. Although the idea of simply driving straight up to reach space might seem far-fetched, it serves as a reminder of the incredible progress we've made in our understanding of space and the possibilities that lie ahead for space exploration, continuing from the notion that reaching space might take just over an hour if you could drive straight up. It's important to consider the numerous factors that make such an ascent far more complicated than it initially appears. Beyond simply reaching the Kármán Line, there are several essential elements to the physical environment that would pose substantial challenges to any attempt to ascend to space. One of the first major hurdles would be dealing with air pressure and atmospheric density, both of which decrease as you gain altitude. As you rise, the pressure exerted by the atmosphere on your body would decrease significantly. This could cause physiological changes like hypoxia, a condition where oxygen levels in the blood drop below normal levels. While the atmosphere at sea level contains roughly 21% oxygen, at higher altitudes, the air becomes thinner, and oxygen levels fall dramatically. At the edge of space, the oxygen content would be negligible. This lack of oxygen is one of the reasons why human space travel requires sophisticated life support systems. Even with the ability to drive straight up, a vehicle would need to provide a continuous supply of breathable air, in addition to maintaining pressure inside the cabin to prevent the body from experiencing altitude sickness. In reality, driving straight up from the Earth's surface would be akin to rapidly traveling through layers of altitude zones that correspond to different levels of atmospheric pressure. For comparison, as we ascend a mountain, we can feel the effects of thinner air, even at relatively moderate altitudes like 2,000 meters, around 6,500 feet. This drop in oxygen would intensify exponentially at higher altitudes, where the air is far less dense. Given that air density directly correlates with drag, any vehicle ascending vertically would have to contend with immense air resistance at lower altitudes. Air resistance acts as a brake on motion, making the task of reaching such high speeds even more difficult. In aviation, aircraft designers must carefully consider the aerodynamic properties of a vehicle to minimize drag. To ascend through the atmosphere in just an hour would require a car-like vehicle capable of withstanding intense forces and extreme speeds while efficiently overcoming atmospheric drag. In practical terms, even the fastest land vehicles, like those designed for land speed records, are nowhere near capable of reaching the speed needed to exit Earth's atmosphere. This illustrates that the vehicle would need a propulsion system vastly more powerful than anything currently on Earth, with a mechanism capable of reducing drag and maintaining stability during such a steep ascent. In addition to the physical forces experienced during such an ascent, we must also take into account the effects of temperature at various altitudes. The air temperature can vary dramatically as you climb. Near the surface of the Earth, temperatures are governed by local weather patterns, but as you ascend into higher altitudes, you move through layers of the atmosphere where the temperature behaves in a counterintuitive way. In the troposphere, which is the lowest layer, temperatures generally decrease with height. However, in the stratosphere, temperatures actually rise due to the absorption of ultraviolet radiation by the ozone layer. As a vehicle ascends, it would encounter not only extreme cold but also potential temperature fluctuations that could cause mechanical issues. The vehicle would have to be insulated and protected from the extreme temperatures of space and the rapidly changing thermal conditions in the atmosphere. While the physical challenges are clear, the mechanics of vehicle propulsion are another vital consideration. As mentioned earlier, traditional cars are not designed to overcome the forces of gravity that act on objects at Earth's surface. Rockets, on the other hand, are designed to do so by expelling exhaust gases at high speeds to generate thrust, a process known as Newton's third law of motion. A car attempting to drive straight up would have to generate an enormous amount of thrust to counter the gravitational pull and to keep moving upward. The required propulsion would need to overcome not only gravitational forces but also the mass of the vehicle itself and the resistance of the air. This is why rocket engines are so powerful, because they must create enough force to break free from Earth's gravity. A traditional combustion engine would be insufficient, as it doesn't produce nearly enough energy to reach escape velocity. A critical aspect to consider when imagining such a journey is the concept of orbital velocity. Achieving space is one thing, but orbiting the Earth requires a horizontal velocity, essentially, the speed at which an object must travel to stay in a stable orbit around the planet. This speed is significantly higher than the speed required to simply reach the boundary of space. To enter orbit, an object must be traveling at speeds of around 28,000 km per hour, 17,500 miles per hour, far faster than anything a conventional vehicle could achieve, even if it were driving straight up. So, while driving straight up might get you to the Kármán Line, it would not allow you to stay in space. This is why rockets follow a trajectory that gradually curves and accelerates, rather than driving straight up, in order to achieve both altitude and the necessary horizontal velocity to orbit the Earth. If the objective is merely to cross into space, without worrying about orbit, the journey through the atmosphere would be relatively short once a vehicle reaches a certain altitude. However, even in a hypothetical scenario where a car could accelerate at breakneck speeds and overcome all the challenges of air resistance, temperature fluctuations, and gravitational forces, it's clear that the most pressing challenge would be the lack of adequate propulsion technology. A rocket-powered vehicle would be necessary to overcome the Earth's gravitational field, with technology akin to that used in space launches today. Another practical challenge would be launch trajectory and fuel consumption. Any vehicle designed to travel directly upward would face the issue of balancing the need for fuel against the force required to maintain constant acceleration. Rockets today are designed to use multiple stages, with each stage containing its own fuel to increase efficiency. By shedding weight as each stage is used, rockets can accelerate more efficiently, something that a hypothetical car driving straight up would not be able to achieve. The vehicle would need an uninterrupted fuel supply or an alternative propulsion system that could continue functioning as it climbed. Finally, reaching space in just over an hour, while fascinating in theory, would not be an easy task without significant advancements in vehicle engineering and propulsion systems. The road to space, whether imagined as a straight drive upwards or a more traditional rocket launch, represents the incredible complexity of the physics that govern our planet and the forces that operate within our atmosphere. Despite the significant technological advancements humanity has made in space exploration, the reality of driving straight to space remains far beyond our current capabilities. However, each step forward in space technology continues to bring us closer to making human space travel more routine, highlighting the complexities, risks, and rewards of breaking free from the constraints of Earth's atmosphere. As we move beyond the concept of simply reaching the boundary of space, the next layer of complexity arises from the human experience of rapid vertical travel. Ascending from the surface of the Earth to space in just over an hour would subject the human body to forces and conditions very different from anything experienced on the ground or even in conventional air travel. One of the most immediate concerns is acceleration and g-forces. Rapid ascent would produce significant gravitational forces acting on the body, potentially many times the force of gravity experienced at rest. Even a few g-forces sustained over a short period can cause physiological stress, impacting vision, heart rate, and blood circulation. Pilots and astronauts undergo extensive training to endure these forces, learning techniques to keep blood flowing to the brain and prevent loss of consciousness. A vehicle capable of traveling straight up to space at extreme speeds would need to mitigate these forces, either through advanced seating design, gradual acceleration profiles, or other technological solutions designed to protect occupants from the intense physical strain. Another factor in this journey is the effect of vibration and mechanical stress. The transition from driving on solid ground to breaking through the denser layers of the lower atmosphere would induce considerable vibrations in the vehicle. In traditional rockets, engineers spend significant effort designing structures that can withstand intense vibration during launch. Materials must be lightweight yet strong enough to resist deformation, while internal systems must remain secure and operational under continuous shaking. A hypothetical vehicle traveling straight up would encounter similar challenges, particularly as it accelerated through turbulent air currents. Even minor oscillations could disrupt onboard life support systems, navigation instruments, and structural integrity. Consequently, the engineering of such a vehicle would be an extraordinary task, demanding innovations in material science, vibration damping, and mechanical resilience. Thermal management is another critical concern as the vehicle moves from the warm lower atmosphere to the frigid conditions near space. While temperature decreases with altitude in the troposphere, it begins to rise again in the stratosphere due to the absorption of ultraviolet radiation by the ozone layer. Once past the stratosphere, temperatures plummet to near absolute zero in the vacuum of space. A vehicle traveling straight up would need sophisticated insulation and heat regulation to ensure that both the occupants and onboard electronics function correctly. Failures in thermal management could result in catastrophic consequences, as extreme heat or cold can compromise materials and human survival. Even modern spacecraft face these challenges, requiring layers of thermal protection and active heating or cooling systems to maintain a safe internal environment. As the vehicle climbs higher, it would enter the mesosphere and thermosphere, regions of the atmosphere far less familiar than the troposphere and stratosphere. In these layers, the air becomes exceedingly thin, and conventional aerodynamics no longer apply. Without sufficient air density, wings and air-based control surfaces lose effectiveness, meaning the vehicle would rely almost entirely on its propulsion system and advanced guidance mechanisms to maintain stability. Navigation becomes an intricate problem, as even minor deviations could dramatically alter the trajectory. For a straight-up journey, the vehicle would need precise orientation systems capable of adjusting in real time to micro-adjustments, accounting for gravitational anomalies, atmospheric turbulence, and Coriolis forces caused by the Earth's rotation. In effect, the vehicle would become part rocket, part satellite, and entirely dependent on advanced technology for its survival. A further challenge of this ascent is the exposure to cosmic radiation as the vehicle reaches near space altitudes. The Earth's atmosphere acts as a protective shield, filtering out most harmful radiation from the Sun and other cosmic sources. As the vehicle breaches this shield, the intensity of radiation increases dramatically. Astronauts on suborbital flights already experience higher doses of radiation than at sea level, and traveling straight up would expose occupants to a surge of high-energy particles capable of damaging cells and DNA. Any vehicle designed for such a journey would require effective shielding, not just to protect electronics but to prevent radiation-induced health effects. Without proper safeguards, even a one-hour trip could pose long-term risks, emphasizing that rapid vertical travel is as much a matter of biology as it is of engineering. Finally, communication and tracking present unique challenges during such a vertical ascent. Ground-based radar and satellite networks are optimized for horizontal and orbital trajectories, not for vehicles ascending straight up at extreme speeds. Maintaining contact with mission control or automated guidance systems would require specialized antennas and transmission protocols capable of handling rapid changes in altitude and atmospheric density. Signal delay, disruption by ionospheric interference, and the loss of conventional radio transmission through thin air would all need to be overcome. In essence, The vehicle would operate in a transitional zone between terrestrial and space communication infrastructure, requiring robust and redundant systems to ensure continuous contact and safety monitoring. The human experience of this journey, then, is defined not only by the mechanical feat of leaving the Earth's surface but by the intersection of physiology, engineering, and environmental hazards. Rapid ascent to space in just over an hour would be as much a test of the human body and life support technology as it would be a demonstration of propulsion and engineering prowess. Unlike conventional air travel or orbital launches, the straight-up approach introduces unique and extreme challenges that would redefine what it means to journey beyond Earth. The intricate interplay of acceleration, vibration, temperature, radiation, and navigation underscores why reaching space is far more than simply crossing an invisible boundary. It is an exercise in harmonizing biology, technology, and physics in a way humanity has never fully accomplished in such a condensed timeframe. As we conclude the journey of contemplating a straight-up ascent into space in just over an hour, we shift our focus to the future potential of such rapid space travel. The concept of reaching space so quickly introduces a paradigm where human travel to space could become more routine, akin to commercial air travel. The dream of space tourism has already begun to take shape with companies like Blue Origin, SpaceX, and Virgin Galactic, offering suborbital flights that provide a brief moment of weightlessness and a view of Earth's curvature. These trips, though much shorter than the hypothetical straight-up ascent, give us a glimpse of what might be possible with advancements in propulsion technology and space tourism infrastructure. However, while these suborbital flights mark a significant step, they still do not approach the speed or capability required to make space travel as accessible as a flight from New York to London. The challenges of rapidly reaching space, such as overcoming gravity, atmospheric drag, and the complexities of maintaining human life at extreme altitudes, would need to be addressed in order to make vertical space travel a reality. This raises important questions about the long-term feasibility of such travel, particularly for the average civilian. If a car-like vehicle could, in theory, drive straight up to space in a little over an hour, it would require monumental advancements in not only propulsion systems but also in areas like passenger safety, life support systems, and vehicle stability. The idea of moving vertically at great speeds opens up new possibilities for human transportation beyond Earth's atmosphere, but also offers new challenges for how we think about human settlement in space. As space exploration advances, the necessity of establishing sustainable infrastructure in orbit, on the Moon, or even Mars becomes increasingly urgent. If space travel were to become as commonplace as it is in our imagination, if vertical ascents could one day be a regular occurrence, then the technology to support space stations, orbital habitats, and long-term space missions would need to evolve dramatically. Space stations like the International Space Station, ISS, already provide valuable platforms for studying life in space. But their scale, design, and capacity are limited. A future where humans can regularly travel straight up to space would require entirely new types of habitats, transportation systems, and support infrastructure to ensure the survival and comfort of space travelers. Looking further into the future, one might also consider the potential for using space as a launching pad for exploration beyond our solar system. The velocity required to escape Earth's gravity is just the first step in a longer journey. Once free from the Earth's atmosphere, the next challenge is achieving speeds that could carry a spacecraft to other planets, moons, or even stars. Current spacecraft are limited by the propulsion systems available. And space travel beyond the Moon requires far more advanced technology. One potential future propulsion system is nuclear fusion, which, if successfully harnessed, could allow for faster travel through space by providing higher energy yields than conventional chemical rockets. While nuclear fusion is still in the early stages of research, it has the potential to revolutionize space travel and make long-distance missions more feasible, possibly even reducing travel times to Mars or enabling humanity to send probes to distant stars within a human lifetime. The commercial and scientific implications of such advancements in space travel are vast. The possibility of a vehicle that could drive straight up into space might initially seem purely theoretical. But as propulsion technology, materials science, and life support systems improve, the line between what is considered science fiction and science fact will continue to blur. Human expansion into space would not only allow for the exploration of other planets but could also lead to the creation of space industries. For instance, mining asteroids for valuable resources, harvesting solar energy in space, and even establishing tourism-based economies on orbiting stations or the moon could open new frontiers for economic growth. In fact, many of these industries are already being explored today, with private companies eyeing the moon, Mars, and asteroids as viable sources of minerals, water, and other essential materials that are scarce on Earth. One of the greatest challenges of this kind of rapid space travel is the environmental impact. Space launches, particularly those using chemical rockets, release significant amounts of carbon dioxide and other pollutants into the atmosphere, contributing to climate change. As we develop more advanced space travel technologies, it will be crucial to consider the environmental footprint of space exploration. Solutions such as electric propulsion systems, the use of sustainable fuels, and even space-based solar power stations could minimize the environmental cost of space travel. Additionally, efforts to reduce space debris, which is already a growing issue in Earth's orbit, would become even more critical as human presence in space becomes more frequent. A sustainable approach to space travel would involve not only technological advancements in propulsion and energy but also a responsible approach to the long-term management of space itself. The social and psychological impacts of regular space travel are also worth considering. Traveling into space in just over an hour would fundamentally change how we perceive both space and Earth. The experience of seeing our planet from space has already been a transformative experience for astronauts, influencing how they view humanity's place in the universe. If space travel were to become as routine as a plane flight, it could foster a deeper sense of connection between people on Earth, transcending national and political boundaries. It could also catalyze a sense of shared responsibility for protecting our planet. As the concept of Earth from space becomes more ingrained in our collective consciousness, it may motivate new environmental policies, global cooperation, and technological innovations aimed at sustaining life on Earth while expanding our reach into the cosmos. Additionally, the broader human experience of space travel might also encourage new philosophical and existential questions. If space were easily accessible, humanity would inevitably confront new questions about what it means to be human, our place in the universe, and our relationship to other life forms we might encounter in space. As our technological capabilities expand, we may also encounter other challenges, ethical dilemmas surrounding the colonization of other planets, interactions with potential extraterrestrial life, and the societal implications of having off-planet colonies. With these new frontiers come responsibilities not only to protect life on Earth but also to carefully consider how we extend our influence into the cosmos. As humanity inches closer to making space travel more accessible, it's clear that the road to the stars is not just about technological advancements but also about preparing for the profound changes that such exploration will bring. Whether we drive straight up, take a rocket, or use entirely new propulsion technologies, our journey into space will continue to redefine what it means to be human and how we live in a vast, interconnected universe. As we look ahead to these possibilities, the next century could witness a profound shift in the way we live, explore, and understand our place in the cosmos.